All right, and recording is running. So Tuesday, August 31st. We're wrapping up the month of August, and we're also going to wrap up linear motion today because tomorrow I want to get you guys going on projectiles. Okay? So projectiles, we're going to go back to 2 dimensions. Trigonometry is going to come back. So let's solidify the linear motion skills because you need linear motion to do projectiles. Okay? So today I'm just going to solve as many problems as I can. I'm pretty much going to pull them off this page with the boxes because I like my questions more than your book questions. I think, I think they're more encompassing. You get more out of those. So that's what we'll do. All right. So did you guys solve the graphs for this scenario? A ball is thrown downward from the top edge of a cliff. Let's call it down the positive direction. Like that. Okay. Now I want to remind you guys a couple of very similar graphs. In fact, if you're in class, you guys see these 2 posters over here. Okay. For the video, I'm going to do some of those. They're basically those posters. Right. Well, part of them anyway. Okay. You guys remember if you drop the ball off a cliff? Position versus time, velocity versus time, acceleration versus time. We've been looking at those 3 type graphs over and over. Okay. And I can start from the middle graph, the velocity versus time. Remember how this ball will pick up speed at a constant rate? So it looks like this, as time tick, 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 goes faster, faster, faster at a constant rate. And that constant rate, which is the slope of this line, is what acceleration is. And if it's free fall, acceleration due to free fall, it's common to call it g. And on Earth, that number is 9.8 meters per second squared. But most of the time, we just round it to 10, about 10 meters per second squared. So if you drop a ball off a cliff, starts from rest, falls faster, faster. It's accelerating at a constant rate, as long as you ignore air drag, which we are. And you guys remember its position versus time takes the shape of a what? Parabola. And in this case, the vertex is right at the bottom, isn't it? 0, 0. Starts at position 0 at time 0. If you define the top of the cliff as 0.0, which is consistent with that. Down is positive, so everything is all positive numbers. You guys remember that? Okay. Then, what if you throw a ball upward? You see the picture on the left side, you guys throwing chucking straight upward. Right? Now, if down is still defined as the positive direction, then wouldn't it be true this guy's throwing it in the negative direction? Right? So you get something like this: velocity versus time. At time 0, the ball is just leaving his hand right here. It's in the negative direction. But as soon as it leaves his hand, it's in free fall. So it's going to start towards the ground with slope g, just like before. Acceleration versus time looks exactly the same as before. Let's put these graphs side by side. Here's just, it drops. Here's he throws it upwards. You guys see the 2 acceleration graphs look the same? In fact, the velocity graphs looks almost the same, except that if you throw it upwards, it starts with a certain velocity. In this case, negative, because you threw it in the negative direction, right? And you see where the curve crosses the time axis on v versus t? Right? Isn't that like 0 speed just at that moment? Right? 0 meters per second? Doesn't that also represent the peak, right, where the ball hit the peak? Right? So if I'm lining these graphs up, x versus t still makes a parabola shape, and the vertex happens to be at that point because that vertex, that represents the time and also of the maximum height, and also what the maximum height is. Right? This graph's like upside down because remember, up is the negative direction, down is the positive direction. Okay, guys remember that? Okay, so that's those 2 scenarios. I wonder if you guys can go this extra step. Figure out, what if you throw the ball downward? Okay. Now, remember, that's not exactly what I just showed you. I just showed you the graphs for if you throw the ball upward. Okay. So now, what if you throw the ball downward? Same 3 graphs: x versus t, v versus t, a versus t. Right. Now, I'm sure you guys have got a start on those already. I'm going to redraw those axes. Give you guys another minute to see what those curves look like. See if you can figure out what those curves look like before I show you what they look like. Because if you can get it, then before I show you, then you should have confidence that you know how to do this. Okay. Give you guys a hint. They're all first quadrant graphs, so none of them go into negative territory. You guys see that's just like first quadrant. Okay. All right. So I have so the scenario is throw ball downward off a cliff. Okay. We're going to say down is the positive direction. Positive direction. That's arbitrary, but we got to pick a direction. So we've been doing this all along. So let's just stick with that. Okay. Once we got that, how far did the ball go in meters? How fast is it going in meters per second? And what's the acceleration meters per second squared? What's meters per second squared? As a function of time is ticking in seconds for every single one of these graphs. Right? You guys figure out what those graphs look like? And if you have a pencil and you mess up, then you can just go back and erase. But if you get it right, you're like, aha, I got it right. And I know what's going on. Right? That's the side. So I just copied the question and the axes over, just blew them up bigger. Right? Right? You guys figure out what these look like? Right, so you're throwing the ball down. Guys, if you're throwing the ball downward, aren't you throwing it in the positive direction because down is defined as positive? Right? So already at time 0, does the ball have 0 velocity at time 0? Yes or no? No, because you're chucking it down. It's leaving your hand. It's already on the move. At time 0, it's already maybe like this fast right here. And I'm going to name that. I'm going to call it V naught. Right? So you threw it downwards. You threw it into the positive direction. You're throwing it in the same direction as gravity is also pulling, right? What does the rest of this graph look like? All right there. And what's the slope of this line? G for like gravity, like Earth gravity, right? And hey, how about acceleration versus time? Meters per second squared. I didn't write that very well. This is read all this. Meters per second squared. That looks like a blob of beep up there. Did you guys do? You guys did this, right? Because extend this a little bit. And reason is that you guys remember the slope of V versus T tells you the coordinate of A versus T. In this case, I'll just call it G for gravity, like whatever the gravity pull is. If this is on Earth, then that would be about 10 meters per second squared, right? That's a constant value, just like that, right? So, okay, so you threw this ball down. It's picking up speed faster and faster. At what rate? Picking up speed at 10 meters per second per passing second, or generically G. You guys have? Okay. All right. Finally, X versus T. Now, over and over again, for free fall situations, for uniform acceleration, X versus T always takes what shape? Parabola. I mean, these two have been parabolas, right? Some piece of a parabola, vertex, vertex. Okay. So some slice of a parabola, right? But you know what else? Is that I remember going from here to here and here to here, the instantaneous rate of change, like the slopes of X versus T, tell you V versus T. And this already starts out with the initial velocity, doesn't it? Okay. So do what I do here, and then I'll fill you on the details as we're going along. Okay. Put a little hash line like that. See that dash line? Okay. Okay. And then what I do is I'm going to draw the curve based on that. Okay. It will be a parabola, but it's like a parabola that's extending from that point, right? Like, see how it's like the ruler is like flush to that curve, tangent to like that dash line at that point. Is that? Okay. Now this is a parabola shape. I'll even label it parabola. It's a slice of a parabola, but do you see the vertex anywhere there? No, mathematically the vertex is like back here. Like if you continue the parabola, it would be like in the past, it'd be like back here. Okay? There's a way to physically interpret that, but what I want to focus on just in this class time is that this dashed line that I just made has a slope, a very specific slope, something that I already wrote somewhere else on this paper. Can anybody figure out what the slope of this dashed line right at the origin is?
Gravity?
Good guess. No, slope of X versus, here, how about units? Is it rise over run, right? Is it some number of meters per second? Meters per second, that describes some kind of velocity. In fact, it's at the initial condition. Hey, do you think that this slope represents this initial velocity? Right? That's exactly what it is. Remember, the slopes of this graph tell you the coordinates of this graph. The slope of this graph tells you the coordinates of this graph. Right? Isn't that? Okay. Okay. Now, we can also go the other way. Okay. You guys remember that the area underneath the curve of A versus T tells you like something about V versus T? Okay. I want to fill you in on some other details about that. Okay. So you guys see the height of this is in meters per second squared, and the base is in seconds. What would happen if I do meters per second squared multiplied by seconds? You guys see 1 second's gonna cancel? It's gonna leave you just plain meters per second. Okay. So what I'm trying to get at is that this here hatched rectangle represents some, now I also almost want to say V, but really what it is like an acquired velocity. I'm gonna call it delta V, which represents change in velocity, right? Sort of like tacking on a little bit of info that I haven't technically told you guys yet, but sort of, right? And how does that line up with these graphs? Here, I think I show you how this lines up. This will make a lot more sense. Okay. Put a dash line here. Okay. You guys see this this change in velocity from initial to final for like some time interval like that? These times are supposed to line up. Sorry about that. It's supposed to like line up right here. Okay, pretty close. Okay. That is the change in velocity. So delta V, you guys know in, that triangle is Greek letter delta means change in. So this actually means change in velocity. Okay, so you threw it at some initial speed, it increased its speed due to falling in the gravity field for some time, which is represented by this your rectangle, and that represents the change in velocity. Okay, guys good? And then for completion, you know that to go from V back to X to figure out how far did the ball fall as a function of time, isn't that what property of V versus T tells you how far? It's not the slope, it's the, what we just did. Something about area. Okay. You guys see a trapezoid right here? See that trapezoid? Okay. Let's break that into a rectangle and a triangle. You guys ready to have your minds blown? You know, blow everybody's mind here. As long as you're awake. Is everybody awake? Watching this? All right. And so if you are, be prepared to be amazed. Let's take a look at this rectangle right here. Call it some generic time t. Okay. What's the area of this rectangle? So just height times base times height. Isn't that v naught times t? So the area of that rectangle right there is change ink color. Let's see what color pens I have. Boom, I choose green. After that. The area of this rectangle is v naught t. Right? Sort of hatch this in. That's v naught t. You guys see that? Okay. And maybe I'll pick purple for this triangle up here. Right? This triangle, isn't the area of a triangle 1/2 base height? Right? So area of a triangle, 1/2 base height. The base is some number of generic seconds t. Isn't the height this delta v? And wasn't that delta v just the area of this rectangle, which is g times t? So that's that. Right, so 1/2 base height, just of the triangle, it's like that. Hey, can I combine those t's? Make that t squared? I got 1/2 gt squared. 1/2 gt squared? Hey, that sounds like something you might learn in college. Right? How far did the ball fall in 5 seconds? 5 times 5 times 5. It's about 125 meters. That's what that is. Right? This is your classic 1/2 gt squared. Right? And oh, look at that. Guys, what's the area of that whole trapezoid? The green part plus the purple part. It is exactly this first amigo right here. V naught t plus 1/2 at squared. The rectangle plus the triangle. Guys see it? Boom. All right, guys ready to solve some problems? Who's got any questions? Any questions? All right, moving on. I think we got a good start to this class. So, like I said, I want to just pull some problems off this page with the boxes. I like my questions more than the book, so that is what we are doing. Let's start with number 1, number 2, that very first scenario. This one is actually the simplest, most straightforward scenario. You guys will see why when we get into it. Next one, you guys have solved this already. All right. It says a baseball is thrown towards from the pitcher's mounted plate. It travels at approximately constant velocity. Now, it's one of those that, well, you know, maybe that's not exactly true. You have to discount air drag, discount that gravity's taking on a little bit. But that aside, we're up in the blimp, we're looking down, that ball goes pretty much constant velocity. We're going to assume that. can you figure out how much time it would take to reach the mound and what's the speed that's crossing the plate? And I gave you the distance between the mound and the plate, which is like the fixed number, right? In terms of feet, it's like, is it 60 feet, 6 inches, something like that. But in meters, since we're doing metric system, let's call it 18.4 meters, right? The fact that the ball is not accelerating, or approximately, can we just take A and set it about equal to 0? So we're going to do that. And let's say we know the throwing speed, right? So maybe we brought a radar gun to this party, and we know how fast the pitcher's throwing, and it's this number right here, right? So my number is like 37 meters per second. Can you figure out how fast the ball's going to cross the plate, and what's the batter's reaction time? Okay, both those things. Okay. Now, even before I get started on this thing, since we're talking about just constant velocity, how many guys think that? You know what? I'm gonna save that question for later. Okay. Let's just let's start going through this. Okay. Okay, so this is number 1 and 2. Okay. Got a plate. Okay. Got a mound. Okay. Got distance is given as 18.4 meters, so that's a known value. Okay. The throwing speed of the ball, I call it V naught, is also a known value. Now, on my paper, it says 37 meters per second, so I'll be using that. Okay. And approximately constant velocity means that acceleration is 0 meters per second squared, right? Oh, whoops. Back up for you guys here. Okay. You guys good? That's the setup. Let's do a tax VB checklist. Right, just to, I know it's already in those boxes, but just good practice just to get a, what do we have? What do we want to know? Right. So I know this is 0 meters per second squared. This is 18.4 meters. And I know this guy's throwing at 37 meters per second. Okay. All right. Maybe let's solve for, well, you guys tell me. Actually, yeah, let's go ahead and solve for time first. Time, right? Now, if you want to solve for time, which equation looks good? First, second, or third? For time.
First.
I like the first one too, right? Because it relates distance to time. We know distance. We want to figure out time, right? See, the problem with the second one is that there would be 2 unknowns. You don't know time or VF. You guys see that there would be 2 unknowns. So if you take that one and dead end, go back. Right? And the last one, well, that one doesn't even talk about time. So that one's not even a candidate. So yeah, first one. Let's do the first one. Okay. So if I write the full thing out, I'll get how far the ball goes is V naught T plus half AT squared. Okay. That's the full equation, the full formula. Okay. But you know what? When I start plugging in numbers, start doing that. Let's do that in blue here. Okay. We know this is 18.4 meters. I know the throwing speed was 37 meters per second. Don't know time. Got to solve for time, right? I figured that out. But hey, what's acceleration equal to?
0.
0. What happened to this whole thing? Yeah, just goodbye. Right? Hey, isn't this just distance equals speed times time? Right? And I know this is maybe an overly complicated way of saying this, but you guys could do this before you even walk in this class. And I know that because I asked you guys, if you're driving towards Jacksonville, you see the sign says how far away Jacksonville is, you know the speed of the car, you can do a calculation ahead, figure out how much time it's going to take to get there. Right? Distance equals speed times time. That works perfectly well as long as you are not accelerating. And I want you guys to see that these equations do boil down to simplified forms that are also true for conditions like this. So you guys see there's going to be one algebra step. I just need to divide both sides by 37 meters per second. That will isolate the time. I'll get time is equal to, okay, so this cancels out here. Whatever 18.4 meters divided by 37 meters per second is, that is, it rounds to 0.50 seconds. That sounds believable. I mean, if you were a batter going up against a pitcher, as soon as the ball leaves the pitcher's hand to where the ball crosses the plate, about half a second. Yeah, that sounds about reasonable, right? Guys got that? Now, the follow-up question was, how fast is the ball crossing the plate? How many of you guys know the answer already? How fast that ball crosses the plate? Who knows? Oh, yeah. What do you think, Ezra? Yeah, it has to be the same as V naught because the ball is not accelerating, right? But if you really wanted to be absolutely formulaic about it, I guess you could pick one of these formulas. Okay. Let's take a look. Maybe I'll just talk about this. Well, yeah. You guys see the second one? VF equals V naught plus AT. Because if A is 0, doesn't this term go point, goodbye? And you got exactly what this rule says. VF is V naught, right? Or if you pick the third one, A0 point, goodbye, square root both sides, same story, right? So I just want you to see those consistent. So final velocity equals initial velocity, which is, on my paper, 37 meters per second. Okay, guys good? Okay. Now that was, that's the only one on that entire paper that has 0 acceleration. Okay. So I think the other ones are more fun. Let's pick one of the more fun problems. Next scenario, number 3, number 4. We got going on here. Says a ball is thrown towards the ground from a treehouse to some given height, reaches the ground some given time. Now, in the past few days, we've been dropping balls from tree houses. Don't remember throwing one yet. Although, this sounds a lot like you guys' starter question this morning, doesn't it? So, you basically have the graph for this already. We just did that a few minutes ago. Can you find the speed that the ball was thrown and the speed that the ball reaches the ground? So, interpreting these numbers, okay, looks like somebody brought a stopwatch, knows how much time it takes to reach the ground. We know Earth gravity, the rate that's picking up velocity. We know the height of the treehouse, x, in meters. We don't know how fast this guy's throwing the ball or how fast the ball is hitting the ground, but those numbers have to be determinable for the ball to reach the ground in this time, this distance, and this gravity. Right? There has to be some determinable numbers associated with this. Right? So I think I'm going to go landscape with this. This is number 3 and 4. Okay. Oh, gotta zoom out for you guys here. Okay. Here's my tree house. Straight line here. Okay, call this the height of tree house X. Got a baseball. There was some V naught initial velocity, so that when this ball is landing on the ground, it's going to be so much faster final velocity. I mean, VF better be greater magnitude than V naught. It's got to be picking up speed. I hope it is. We're going to find out. Right. We know gravity's pulling down at 10 meters per second squared. Since I'm labeling stuff, what was the height of my tree? My tree was 8 meters tall. Your guys' tree is probably a different number. 8 meters. Right, so I have an 8 meter tall tree house. Right? I know gravity's pulling. Well, I'm going to use 10 meters per second squared on my notes. Right? And also, this guy down here brought a stopwatch. And I'm getting time is equal to, okay, my paper says 0.7 seconds. 0.7 seconds. Okay? That's 1, 2, 3 known values. Okay? And then I just got to solve for how fast did he throw it to get to the ground, 8 meters in 0.7 seconds. And also, how fast was it traveling when it got there? Okay. Okay. In the graphs that you guys just put together, basically these graphs describe that situation too, don't they? Okay. All right, well, let's do the equation version. All right. For completion, do this. Right. Don't know this guy, don't know this guy. 8 meters, 0.7 seconds. 10 meters per second squared. Okay. Time to bring in the 3 amigos. So which one do you guys want to start with? First, second, or third? First. I like the first one also. Yeah. Here's why. Because the first one, okay, we can solve for V naught, but we know everything else. Versus, you guys have the second and third ones? They each have starting and ending velocities, which are both unknowns. So by themselves, you definitely can't get it. It'd be dead end. Maybe together, but that'd be fun. Let's use the first one. That's the most straightforward way. First one. I'm gonna go, how far did the ball fall is equal to V naught T plus half AT squared. All right. Let's just start plugging stuff in. Right, so I got 8 meters, the ball went. I do. A second. Let me take care of, here. See if you can beat me to the answer. See if you can beat me to the answer. If you can beat me to the answer, then you should have confidence that you know how to solve these. I'm starting to put quizzes together, so haven't finished writing quizzes yet, but have to solve some problems like this. Let's see. V naught, I don't know. All right, time was 0.7 seconds plus 1/2, 10 meters per second squared, is 0.7 seconds being squared. Because that's squared, does that apply to the 1/2 AT, or does it only apply to the T? Yeah, only the T. Right? The only thing that's being squared is the 0.7 seconds. Okay. Right. I'll clean this up a bit. So 8 meters equals 3.7 seconds, V naught, plus, right. Notice everything's plus. I have no negative numbers. I mean, gravity's pulling positive direction, you threw it in the positive direction. Okay. This collectively comes out to this many, and then the unit would be meters. Right. Sometimes it's good to do a unit check. See, I have 3 terms at this point, boink, 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 3 terms. Okay. That's a meter, that's a meters. Velocity is meters per second. If I multiply it by time in seconds, that would also give me meters. So they're all meters, so that's good, because you can only add together like terms, same units. I'm gonna, you guys see how to finish this off algebraically? You guys subtract off 2.45 meters from each side. It's gonna give me, what is 8 minus 2.45? 5.55 meters is equal to 0.7 seconds times V naught. Okay. Divide both sides by 0.7 seconds. Okay. Cancels out over here. That's 5.7. I'm getting 7.93 meters per second is the throwing speed. 7.9. All right. Yeah, it's a number on my paper, so all good. Okay. Guys good? Pick up. Right. Now, great, we got this number. Check. Now we know the throwing speed. Right. There's still one more thing we gotta do. We gotta figure out, I wonder how fast this ball is hitting the ground. Right? I mean, it's gotta be more than this. It's been speeding up all the way, right? Which one do you guys like, first, second, or third? Second. Good choice. Now, first one doesn't say anything about VF. You could have picked either the second or the third. So yeah, let's definitely do the second equation. That's probably the fast way to do it. Right. So hold on to this, just continuation. Gonna go final velocity equals initial velocity plus AT. Okay. Solve for that. EF equals. Okay. This number is this number. So I just did a bunch of work to figure that out. It'll be meters per second. Plus this is 10 meters per second squared. Time. Now the time is given. Remember, there's a guy with the stopwatch here. Okay. So the whole time they have this measured time, so many seconds. Okay. About to get it. All I have to do is throw that in the calculator. So what is 7.93 plus 10 times 0.7. Okay. Also the units match. Meters per second. And then meters per second squared times seconds is also meters per second. 14.9 meters per second. That's it. Okay. And that's the number on the page, so that checks out. You guys good there? Right, any questions? Okay, next scenario. So we're doing here on, let's go 11, 4, 14. Okay, good down, right? Okay. Let's look at number 9, 10. Number 9, 10 down here. Okay, zoom in. Okay. It says a ball is thrown straight down I give it an initial velocity from a tree house of some given height from the ground. Oh, so we got another tree house. I'm throwing another ball down. This is a lot like the last scenario, except there are different variables that we know this time. Okay? But those graphs that we put together at the beginning of class, same application. Like all these, let me zoom out for you guys. But all these graphs are also going to describe the scenario that we're also about to do. Okay? So what do we know here? Okay, so this time, nobody brought a stopwatch, so we're not quite sure the time, but we're going to solve for that. Okay. We know that the rate that gravity is pulling down. For my notes, I'll call that about 10 meters per second squared. We know the height of the treehouse. It looks like I'm using the same treehouse. Okay. But this time, somebody brought a radar gun. That's what we have instead. Instead of bringing a stopwatch, we brought a radar gun, so we can know the throwing speed. Okay. And then, pretty same story. Okay. Now, of course, the adventure there is going to be a little bit different because our known values are a little bit different. But it's a very similar story. Same tree house as before. It's 8 meters up in the sky. Say x equals 8 meters. This time we know the throwing speed. Say v naught equals, grab the number right off my paper. It says 2 meters per second. Okay. So not very fast, but just kind of lob it down like, ugh, right? It better be hitting the ground a lot faster than I threw this thing. So let's come down here. Little motion marks. Okay. And this time, here's this friend down at the base. Okay. Did not bring a timer, but brought a radar gun. You draw a radar gun. There's a radar gun. Okay. That's how we know that number. Because the radar gun. Okay. And of course, gravity's pulling down at, let's call it 10 meters per second squared, just for the notes. Okay. So do checklist. Okay. Don't know this guy. I'm going to call this guy about 10 meters per second squared. I know the height of the tree was 8 meters. And I know I threw this thing at 2 meters per second. Okay. All right, got to figure out how much time to reach the ground and how fast it's going at the ground level. Now, there's a couple ways you can approach this, and I want to take you guys through both. Right. So think about how you would do it, and then I'll just take you guys on 2 different adventures, and we're going to end up at the same place at the end. Okay. One way you could do it is you could go to this top equation. Just look at this. You know everything except for t, so you could solve it. Okay. Now, if I do it this way, who sees what math process I'm about to run into starts with a Q? Quadratic. See, if you want to extract t, I got a t squared and a t and some other number floating around. Okay, this will be a quadratic situation. After I take you guys through this process, I'll show you guys how you can actually solve this by skirting around the quadratic, but you'll get the same answer in the end. So do quadratic first. So I've got x equals v naught t plus half a t squared. My journal, right? Start plugging in numbers. I know this thing went 8 meters. I know I threw it at 2 meters per second. Don't know time. Plus 1/2 10 meters per second squared times time squared, right? Okay. Now, do you guys remember? Here, we put. How should I do this? I'll put this on a note card. That's what I do. Okay. Here's a quadratic. Okay. So if you have something in this form, like ax squared plus bx plus c is equal to 0, that's part of the form, right? If you can get it like this, equal to 0. Okay. And you're trying to extract x, which is almost what we have here, isn't it? Just have to rearrange it to make it look like this. Then x equals, does anybody remember what it is? Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, you guys remember that? Right. I'm going to use that. I'm going to slide this card right over here. Right. I need to put it in that form, so rearrange some things. Half of 10 is 5. I'm going to say 5t squared, right, plus 2t, here's the unit, okay, minus 8, because I need to subtract the 8 meters over. Okay, that's equal to 0. That puts it in this form. right? It's like that. Okay, and then I can say then that t equals, got here, negative b, so that's negative 2. I'm going to leave the unit off just to save a little bit of ink here. Right, plus or minus the square root of b squared minus 4ac. Now careful, there's a bunch of negatives floating around, so be careful with your arithmetic. Right, I'll divide by 2a. That's exactly what that would be, right? Now notice there's a plus or minus, which means it could actually give us two different answers, right? Which one do you think is going to be the correct answer, the plus one or the minus one? You're right to say plus. Now, sometimes you could have a scenario where it actually is minus, but here's why it has to be plus. Right, so it's going to be a very short time in the future, but if you look at that motion, like just falling faster, and then you reround the clock like you ran the film backwards, except instead of guy throwing it, you went ahead and just said, well, what if it just like the prevalent from the past? There would be a time in the distant past where it also would have been at ground level. Or if you want it like this guy throws the ball, they fall side by side, all the way down. Okay. That would be what the minus one would be. So you get a big negative number, means a long time in the past. We're not interested in that one. We want to know the short time in the future. And it better be, this better come out positive overall. I got negative 2 plus something. It has to be positive because we're looking into the future. Right. We're going to find out. Right. So negative 2 plus square root 2 squared. Oh, I have a couple of negatives here. We cancel those out. Got minus and negative. That's plus. So plus 4 by 5 by 8. Close that whole top. Divide by 2 times 5 is 10. Okay. I'm looking at this number right here. 1.08 seconds. Okay. That's it. Okay. Okay. So it's just using those equations. Top one specifically. Now you have to know quadratic, right? Or do you? I did tell you guys I was going to show you guys another way you could get to the answer without going through quadratic. Okay. So we do that. And that involves going through VF. Now VF, I could have actually solved that first. You guys see this third formula? Right? Notice it has everything we need except for VF. I mean, we know these other three values. These were given values. The throwing speed, the earth gravity, the height of the tree. Those are all known, aren't they? Right? So I could have started with that, and that's what I'll do, just to solve for VF directly. Right, so let's go back to the start. I got final velocity is equal to initial velocity plus AT. I know through this thing at 2 meters per second, it was speeding up at a rate of 10 meters per second. And it did that for, oh, I'm so sorry, guys. I meant the third equation, because assuming we didn't have t at that point. Okay. Start over. VF squared equals V naught squared plus 2ax. That's what I meant to pick. Right. So we're trying to figure out how fast this thing crash landing. Knew it threw this thing at 2 meters per second. (10 meters per second squared), it's accelerating towards the ground, and the height of the treehouse was 8 meters. Okay, that's solvable. Right. Just pop that in the calculator. 2 squared plus 2 by 10 by 8, 164. Now VF squared is 164 meters squared per second squared. Keep track of the units, square root both sides. I'm getting the crash speed is 12.8 meters per second. Okay, is that? Okay. So now I've got everything, right? Went about one way, got time is 1.08 seconds. Went about another way for final velocity, got 12.8 meters per second. Is that? Okay, now here's where everything's going to come full circle. I told you guys I was going to show you how to get this time without going through this quadratic stuff. You guys ready to see that? That's where we're going to break out the VF equals V naught plus AT. Okay? That's the second equation, isn't it? The second equation. Okay. We're going to take this VF, pop it right in here, because we just solved that. We just found it. What's that number? So I got 12.8 meters per second. I know I threw this thing at 2 meters per second. That was a known value. Remember, the guy bought the radar gun. That's why he has a radar gun. Where that came from. It's a given value. picking up at 10 meters per second squared. For some time, hey, you guys see that we can definitely solve time without doing all that quadratic stuff now, right? Usually different ways to approach these problems. Right? You guys see we subtract 2, divide by 10, so subtract 2, that's 10.8 meters per second is equal to 10 meters per second squared t. Divide both sides by 10. You don't even need a calculator for that, do you? Just roll the decimal. That is, the number 1.08 meters per second divided by meters per second squared gives you seconds to represent time. Hey, 1.08 seconds? What did we get before doing all that quadratic stuff? 1.08 seconds. Boom. 2 different ways to get there. Same thing. So, yeah, you guys have multiple ways to solve these things. Okay. You guys good? So, yeah, now we know everything about the motion of that. Okay. The last one I want to do with you guys today, the last scenario, is number 11, number 12. Okay. Any questions so far? Ready to move on? All right. Last scenario, 11 and 12. Got a car brakes to a stop. Ooh. We've done some of these last few days. Car brakes to stop. Let's say take some given time. Right. So somebody's watched this car brake to stop. Was timing it. Takes maybe like 3.5 seconds on my paper. Let's say you know the rate that the car can slow down. So you have a given acceleration. Now, in future weeks, you'll see that you can actually figure this out if you know like certain material properties, like the tire and the road, asphalt road. It's related to something called the coefficient of friction. That's future stuff. Right? And then final velocity, of course, would be 0 because the car is braking to a stop. Right? Even if I did not explicitly give you that number, you could probably figure that out. Final velocity's got to be 0. Okay? All right, so get rolling on this. Let's decide. All right, and paper. I'm gonna draw this out. So this is number 11 and 12. Okay. Got a car on a road. My road be straight. Because it's like a straight road. Okay. Comes to a stop right here. And well, this is what we got. One thing. Oops, sorry, I got it back up for you guys. Okay. This is one thing we got to figure out is what is this distance x? We don't know it. Right? But we do. The other thing we don't know is we don't know what is this driving speed. Right? Two things we don't know. We don't know that. We don't know that. Okay. So your tax VV checklist. Oh yeah.
Are these problems the ones that are due on Friday?
Yeah. All right. So what do I know? Somebody brought a stopwatch, and my car looks like took 3.5 seconds to come to a stop. It was slowing down at a rate of, well, on my paper, 13 meters per second squared, which is probably as much as you could ever slow down. I guess this is actually a little bit more magnitude than gravity. Even gravity is like 10 meters per second squared. And comes to a complete stop means this number is 0 meters per second. I wonder how much road the car covered and how fast was the guy driving in the first place. Right? So, let's break out the three amigos. Which one looks like it's going to solve something for us? What do you guys like, first, second, or third? Second? I like the second one also. Yeah, because we can figure out the initial driving speed from that and then work our way from there. Like I said. So, let's go. Final velocity equals initial velocity plus AT. Gonna plug in, no, this goes to 0. We don't know if not, solve for that. And it's slowing down at a rate of 13 meters per second squared. So I'm calling it negative, right? Because car's going forward, slowing down, has negative acceleration. And somebody brought a stopwatch, so I know how much time it was screeching for. Right? Here's what I'm going to do. I'm just going to multiply this and then just add it to the other side. And that'll give you not. It's just whatever that is, whatever 13 times 3.5 is. And it would turn back positive, which is good because you guys drive in the positive direction. Right? That's why acceleration is negative, slow down. 45 meters, about 45 something meters. Woo! That's a good distance right there. That's almost half a football field. Okay. Okay, and then finally, the other part of this question was, well, I'm so sorry, that's meters per second. That's how fast he was going. So everything's right. I just got the unit wrong. Okay, we're back. That's how fast he was driving. This, by the way, comes out to about 100 miles an hour, so this guy's definitely speeding. I wonder how much distance he covered. We could use either the first or the third equation to get it. Let me try the third one. Let's do final velocity squared equals initial velocity squared plus 2ax. I'll try this out. Okay. I wonder how much road he covered. We know that came to stop. Started up. There's his initial velocity right there, 45 meters per second. Now it's being squared. He's slowing down at a rate of 13, so 13 is negative meters per second squared times x. Okay, guys, yeah? Okay. So 2 algebra steps. I'm going to take this 45 squared number and subtract it over. After I do that, I'm going to divide by this 2 times 13. Can you guys do those 2 algebra steps? Okay, do that again, because those about to ring otherwise. I'm going to subtract the 45.5 squared over, so 45.5 squared, subtract that over, then divide by negative 26, because 2 times negative 13 is negative 26. Okay. And also I'm running out of paper. So do the algebra, you'll get 79.6 meters. Yeah, that's actually most of a football field. Okay. I can believe that, because if the guy is if he's speeding 45 meters per second, that's about 100 miles an hour. Yeah, probably takes about that distance to come to a stop. Okay. Any questions from today? Any questions? All right, and bell's gonna ring in a few seconds, so we'll stop the recording right there.